Good morning. Today's topic waves. Last chapter of first year syllabus. So in the waves are two types: mechanical waves, electromagnetic waves. Electromagnetic waves can travel through medium and in vacuum, but mechanical waves can travel only through medium. Example of mechanical waves, sound waves. Sound cannot travel through vacuum. What is velocity of sound on the surface of moon? 0, because on the surface of moon vacuum is there, so sound cannot travel. Okay, and in lower classes we proved bell jar experiment, velocity of sound through vacuum is 0. Bell jar experiment, we know that. Now mechanical waves we are discussing. There are two types. So mechanical waves are two types: longitudinal progressive waves and transverse progressive waves. Transverse waves means when wave is traveling, particles are vibrating perpendicular to the wave propagation. In the longitudinal wave, when wave is traveling, particles are vibrating parallel to the wave propagation. And in transverse waves, crust and troughs are formed. In the longitudinal waves, compressions, rarefactions are formed. Both these two waves are called progressive waves because they can travel into the infinity long medium and they never returns to the origin. Now the question is the progressive wave. How to represent a progressive wave? First point, representation of a progressive wave. Y is equal to A sin omega t minus kx. This is the representation of a progressive wave, where A is known as amplitude of oscillation of the particles. When wave is traveling in the medium, particles of the medium are vibrating with an amplitude A. And Y is displacement of the particle at time t. Omega is known as angular frequency, that is 2 pi root of capital by capital D, where capital T is a time period. 1 by time period is known as frequency. 2 by n, already we learned in SHM also. And the K is known as angular wave number, that is 2 pi by lambda, where lambda is called wavelength. The distance travelled by the wave during the time period is called wavelength. Both the longitudinal waves and transverse waves represented by this curve. This curve is called sine curve, because the y-axis we are taking displacement and x-axis we are taking the time. The periodically the particles time is changing, the particles displacement is changing periodically. So periodic motion or simple harmonic motion is represented by sine curve. This is called sine curve because sine and cos values also can change periodically. Sine 0 0, sine 91, again sine 180 0, sine 270 minus 1, sine 360 0. So cos values also like that, maximum, minimum changing. That's why this is called sine curve. So a progressive wave is represented by this. It is not for a transverse wave, compression, crust and troughs are there, transverse wave not like that. This is the progressive wave representation. Okay, and the progressive wave can represent like this also. Y is equal to A sin kx minus omega t. Like that also you can write with the particle started from extreme position. You can write if your particle is going like this, you can write like this. If the particle started from extreme position, that means the particle started from extreme position like this. If you say, you can write it as a cos function. So y is equal to A cos omega t minus kx. Like that, a progressive wave can represent. So this is the progressive wave representation. In this, A is known as amplitude, omega angular frequency, k is known as angular wave number. So that is 2 pi by lambda. From this equation, velocity of the wave v is equal to omega by k, that is equal to n lambda, because omega 2 pi n, k is 2 pi by lambda, 2 pi cancel, we are getting n lambda. Velocity of the wave. Velocity of the particles are different. Particles are essential. Wave is traveling in the infinity medium. So, first topic, representation of progressive wave. And a progressive wave can transfer energy and momentum of the particles. Progressive wave can carry energy and momentum also. So when wave is traveling, momentum is transferring and energy is transferring in the progressive wave. Progressive waves are two types: transverse progressive waves and longitudinal progressive waves. If two progressive waves are in opposite direction and interfere, we get stationary waves. Second one, stationary waves or standing waves. These are also called standing waves. Stationary waves or standing waves. So condition is two progressive waves of same frequency. They must have same frequency moving in opposite direction. This one going this way, this one is going this way. Then they interfere. We get a stationary wave. When the stationary wave is formed, first point, the medium vibrates in the form of loops. These are called loops. All particles in a loop are in same phase. All particles in a loop are in same phase. In the next loop, they are in opposite phase. Hence, the phase difference between two particles in successive loops is pi radians. And one more important point, when the stationary wave is formed, nodes, antinodes are formed. The points where the displacement of the particles are zero are called nodes, and the displacement of the particles are maximum are called antinodes. Nodes and antinodes are formed in the stationary wave. And the stationary wave confined to a limited region, it does not propagate energy. In the stationary wave, energy does not propagate, but in a progressive wave, energy and momentum can propagate. How to represent a stationary wave? The stationary wave is represented by y is equal to 2a cos kx sin omega t. This is the representation of stationary wave. 2a cos kx is known as amplitude of the stationary wave. Amplitude is maximum at antinodes. So here amplitude is maximum. 2a is called amplitude of the stationary wave. Maximum displacement is called amplitude of the stationary wave. And this 2a cos kx represents the displacement of the particles in the stationary wave. This is the stationary wave. And omega is equal to 2 pi n. And k is equal to 2 pi by lambda. Here lambda and n frequency and wavelength are corresponding progressive wave frequency and wavelength, because stationary wave cannot have wavelength or frequency. So this is the second topic, stationary wave. Next, transverse waves can travel through stretched wires only, stretched strings only. They can travel through stretched strings. A string is stretched and vibrated, then the wave traveling is known as a transverse wave. Transverse wave. What about velocity of a transverse wave? Velocity of the transverse wave is root of p by Where T is tension in the string, mu is called linear density. Linear density. That means mu is equal to mass of the wire by length of the wire. Mass by length units kg per meter. Linear density. And we can write linear density as mass of the wire means volume into density by length. Volume means pi r square L d by L. L cancel, we get pi r square d. This is the linear density. So a transverse wave can be written as velocity of transverse wave root of t by mu, root of t by pi r square d, or root of mg by mu. You can write mg by mu also. So this is about the transverse wave velocity. Actually, one wire is connected to a load and the wire is passing over a pulley kept on the table. So it creates some tension. Tension T is equal to mg. So the wire having tension and linear density. So when it is plugged here, transverse wave is traveling through it. Velocity of transverse wave formula is this. What about frequencies of this vibrating string? So string is fixed between two rigid supports. Length of the string is L and plugged in the middle. So first possibility, the first mode of vibration, it can vibrate with a single loop. Both ends nodes are formed, in the middle antinode is formed. Therefore the length of the string L is equal to lambda by 2. Because the distance between two nodes is lambda by 2. Lambda is the wavelength of the wave. Therefore lambda is equal to 2L. Therefore, the frequency of the vibrating string in the first mode of vibration, this is called first mode of vibration. First time the string is vibrating like this. N is equal to V by lambda, that is equal to 1 by 2L into root of T by mu. This is N is called fundamental frequency or first harmonic. N is the fundamental frequency of first harmonic. In the second mode of vibration, second time the same string can vibrate with two loops. Because closed ends always nodes are formed, hence it is vibrating with two loops. One loop, two loops, three loops like that. In this case, the frequency N1 is equal to 2 by 2L root of T by mu. That is equal to 2N. So the frequency is double the fundamental frequency, and this N1 is known as second harmonic or first overtone. It is called first overtone. In the third mode of vibration, that means the next time, the same string can vibrate with three loops. It is vibrating with three loops. Therefore, the frequency in this case 3 by 2L root of T by mu, that is equal to 3M. And the frequency N3 is called third harmonic or second overtone. So this is fundamental frequency, this is first overtone, second overtone, third overtone, like that will come. And fundamental frequency is N, it is 2 times, so second harmonic, it is 3 times, so third harmonic. Therefore, in a vibrating string, the ratio between fundamental frequency and overtones are in the ratio 1:2:3, etc. So this point is an important point. General formula for vibrating string frequency P by 2L root of T by mu. where B is the number of loops. So first mode of vibration 1 loop 1 by 2L, second mode 2 loops 2 by 2L, 3 by 2L, like that will come. Next about we come to longitudinal progressive waves. Longitudinal waves can travel through solids, liquids and gases also. Velocity of longitudinal wave, velocity of the, example for longitudinal wave is sound wave. Sound wave. Sound can travel through solid, liquid and gas. Solid, velocity of sound root of y by d, where y is known as Young's modulus. Velocity of sound in liquids, V is equal to root of K by D. K is known as bulk modulus of the liquid. In gases, velocity of sound V is equal to root of gamma P by D. This is called Newton Laplace formula. Actually, Newton proposed P by D, Laplace corrected that is gamma P by D, and the sound traveling through air is adiabatic process. That's why gamma P by D. Gamma is the ratio of the specific rings, Cp and Cv ratio. Gamma means. Next, velocity of sound in gases can change with the temperature. So, V is equal to root of gamma Rp by m. M is the molecular weight of the gas. Therefore, velocity of sound is directly proportional to square root of absolute temperature. Therefore, V1 by V2 is root of T1 by T2. Therefore, V naught is the velocity of sound at 0 degrees centigrade, and at T degrees centigrade, velocity of sound is Vt. Substituting here, we get Vt by V naught is equal to root of T plus 273 divided by 273. So, by simplifying, Vt is equal to V0 into 1 plus T by 546. Approximately, we can get this formula by using binomial expansion. We do this one. So, 1 plus T by 546. So, as the temperature increases, velocity of sound in the gases increases. In the air, velocity of sound at 0 degrees centigrade is 331 meter per second. With increase of temperature by 1 degree, velocity of sound can increase by 0.6 meter per second. Velocity of sound can increase 0.6 meter per second. And velocity of sound in the gases is independent of pressure, because the root of gamma P by D, if P increases, D also increases. So P by D constant. So velocity of sound is independent of pressure. At a constant pressure, velocity of sound is inversely proportional to square root of density of the medium. Square root of density of the medium. Density is less, velocity of sound will be more. Next about these longitudinal waves, that means sound waves, is allowed to pass through closed pipe and open pipes. So the third topic is closed pipe and open pipe. A pipe which is closed at one end and open at the other end is called closed pipe. A pipe which is open at both ends is called open pipe. First time, actual cord is vibrated and kept here. The air column is vibrating. Stationary waves are formed because waves are reflecting here, and the stationary waves are formed. In the first mode of vibration, the air column can vibrate with the half loop. Here antinode, here node. The distance between node and antinode is lambda by 4, that is equal to length of the closed pipe L. Therefore, lambda is equal to 4L. Therefore, frequency V by 4L. So, this N is called fundamental frequency. Fundamental frequency of first harmonic. Next time, the air column can vibrate. In the closed pipe, the air column can vibrate with 1.5 loop. Antinode, node, antinode like this. And then load here. Therefore, in this case, the frequency N1 is equal to 3V by 4L, that is equal to 3L. So, the second mode of vibration, we are getting third, it is called third harmonic, because 3 times the fundamental frequency. Third harmonic or first overtone. This is called first overtone. Second harmonic, third harmonic or first overtone. In the next mode of vibration, that means the third mode of vibration, the same closed pipe can vibrate with 2.5 loops. The air column is vibrating with 2.5 loops, antinode, antinode, antinode. Frequency M2 is equal to 5V by 4L will come. And N2 is equal to 5N. That means the fifth harmonic or second overtone. Therefore, in closed pipe, the ratio between fundamental frequency and overtone is 1:3:5, etc. There is no even harmonics, only odd harmonics. First harmonic, third harmonic, fifth harmonic present in the closed pipe. Now we can go to open pipe. Open pipe means the pipe which is open at both ends is called open pipe, and pipe which is open at both ends is called open pipe. And in the first mode of vibration, the air column can vibrate with the 2 half loops. The air column is vibrating with the 2 half loops. The first mode of vibration. Antinode, antinode. Because open ends always antinodes are formed trivial node. And the length of the pipe is L, open pipe. Pipe which is open at both ends is called open pipe. Therefore, lambda by 2 is equal to L, lambda is equal to 2L, and is equal to D by 2L. And is the first harmonic or fundamental frequency. And is the first harmonic or fundamental frequency. In the second case, second time, length of the pipe is L, it is vibrating with 2 loops. So this is known as the frequency in this case. N1 is equal to 2V by 2L, that is 2L. So second harmonic or first overtone. This is the first overtone. And third mode of vibration, the air column is vibrating with 3 loops. 2 full loops and 2 half loops. That means 3 loops. In this case, frequency N2 is equal to 3V by 2L, that is 3L. So this is third harmonic or second overtone. Therefore, the air column can vibrate in the open pipe having the ratio of fundamental frequency and the overtone is to 1:2:3, etc. Just like in a vibrating string. So vibrating string, closed pipe, open pipe, we discussed it. Next about echo. One sound is produced here, it is reflected from an obstacle. The reflected sound is called echo of the direct sound. This is the direct sound, this is reflected sound. So this is called echo of the direct sound. Suppose after t time we heard the echo, distance of the obstacle is d, then 2d is equal to v into d, where v is velocity of sound. Because sound is scalar, velocity of the sound is scalar, so total distance traveled 2d is equal to v into d. Therefore, the distance of the obstacle to heard an echo is equal to v into p by 2. So So by using this principle, we can calculate the depth of the ocean also. If we send this is the ship, if we send the waves into water and they reflected and coming back, so then the depth of the lake is equal to, depth of the ocean is equal to V into T by V. So velocity of sound in water you have to take here. So by using this technique we can identify, we can measure the distance of the hills or distance of the some places, terrorist activities in the forest areas, like that we can calculate. So V is equal to Vt by 2. And this method is called sound navigational rating, sonar method, sonar. So that is the use of echoes. Next about beats. Two sound waves of slightly different frequencies. They have slightly different frequencies and they are going in same direction or opposite direction, interfere. Then we get a waxing and waning of sounds in regular intervals of time. This phenomena is known as beats. So high intensity, low intensity, high intensity, low intensity. We can get it repeatedly. So this phenomena is known as beats. Beats mean one waxing and one waning is known as one beat. One waxing, one waning is known as one beat. Because of interference only we are getting. Actually, two sound waves interfere. The resultant wave can be written as 2A sin cos n1 plus n2 by 2, n1 minus n2 by 2 into t sin n1 plus n2 by 2 into t. 2 by here also 2 by. This is the resultant wave. So, during beats, first point, the resultant sound frequency is equal to n1 plus n2 by 2. During the beats, frequency of sound n1 plus n2 by 2. And the number of beats per second, number of beats per second is known as beat frequency. That is called beat frequency. That is equal to difference of parent frequency n1 minus n2 or n2 minus n1. And one waxing and one waning is called one beat. And the maximum number of beats heard per second is 10 only. Maximum number of beats heard is equal to 10, because the persistence of hearing 0.1 seconds. That's why maximum we can receive 10 beats only. Number of beats produced may be different. N1 minus N2. Number of beats produced per second, N1 minus N2. But human beings can receive maximum 10 beats only. So these are about the beats. Next, last topic is the Doppler effect. Doppler effect. This is the source of sound, this is the observer. Both are at rest, then sound waves reaching to the observer having frequency m. If observer and the source are in motion, observer or source are in motion or both are in motion, that means there will be relative motion. The distance between them can change. And they are moving with velocities of v0 and vs, and both are approaching. In that case, the frequency received by the observer is different from original frequency. This phenomena is called Doppler effect. The frequency received by observer is called apparent frequency. Apparent frequency when both are approaching, n dash is equal to m into v plus Vo by V minus Vs. So this is a apparent frequency formula. N dash is equal to m into V plus Vo by V minus Vs when both are approaching. Then sign convention. Towards positive, away, negative, towards positive, away, negative. That means source is at rest, observer is in motion, observer is moving away. Observer moving away means this value is negative. Then apparent frequency m dash is equal to n into v minus VO by V, because source is at rest, V is 0, observer moving away, negative, put the negative value here. And the source is moving away, observer is at rest, m dash is equal to n into V by V plus Vs, because source is negative, that one if we substitute here, V plus Vs will come. So these are the topics in Doppler effect. Doppler effect is asymmetric in sound. If a source is approaching observer with velocity 10 meter per second, or observer is approaching source with velocity 10 meter per second, the frequencies received by observer are different. They are not equal. When source is approaching observer, stationary observer, n1 is equal to n into V by V minus Vs. And when observer is approaching the stationary source, n2 is equal to n into V plus VO by V. So that's why you get different frequencies. That's why Doppler effect in sound asymmetric. And there should be relative motion between source and observer to get the Doppler effect. Suppose the source is at the center, observer is moving around it. You don't get the Doppler effect because the distance between them is not changing. If the distance between them changing, then only Doppler effect is applicable. So these are the topics of waves. We can see the problems in the next video. First one, progressive wave. Second one, stationary wave. Third one, velocity of transverse wave in the stationary string. Next one, fourth one, velocity of longitudinal waves in solids, liquids and gases, temperature effect, pressure effect, etc. in gases. Next, open pipes and closed pipes. Open pipes, closed pipes, their fundamental frequencies and overtones. Next, echoes. Next, beats. And last one, Doppler effect. So many topics are there in this chapter. That's why we covered somewhat little bit faster. So just note down the basic formulas, then we can do the problems. In the next video, we can go for the problems. Okay.